Hello guys, how are you today? So today I'll be explaining chemistry, like AP Chemistry Chapter 1. We have the full course revision questions, which are from question 1 all the way until question 24. So let's start by doing what? By doing question 1. An experiment was conducted to deduce the charges and masses of subatomic particles of atoms by passing the subatomic particles through a constant electric field. Now, as you can notice over here, we have that A deflected the most, B does not deflect, and C deflected, but it deflected a bit less. What can we infer from this? First of all, A is being deflected to the positive side, means it has a negative charge. C is being deflected to the negative side, meaning it has a positive charge, because negative is attracted to positive and positive is attracted to negative. And B is not attracted by either, meaning that it has a neutral charge or zero charge. Now, why did beam A deflect the most? We said that beam A was negative, and the negative subatomic particle that we dealt with was an E- electron. Now, an electron has the smallest mass out of all of the subatomic particles. So neutron has 1, proton has 1 as a mass, but electron has 1 over 1836. It's a really tiny mass. So because it's really tiny, a very tiny mass, it's going to be easier to deflect it. It's going to be easier to change its direction. Now, why didn't beam B deflect at all? We know that beam B didn't deflect at all because it's neutral. It does not have a charge. Now we'll go down to part B. Complete the table below. We need to write the symbol of electron, which is E-, of neutron, which is 0, and of the proton, which is P+. Now let's find their relative masses. This is 1 over 1836. This is 1, this is 1. And the relative charges, this is -1, this is 0, and this is +1. Very simple, very easy. We'll move on to part C. A beam of subatomic particles was passed through an electric field as shown in the figure. So, what can we see? We can see that this is a beam of subatomic particles. We have protons going down. Protons are positively charged, meaning they are attracted to negative. B is 0 because it's not being attracted to either the positive or the negative side. And A, if this is protons, then A is definitely what? It's definitely electrons. And this leaves us with what? This leaves us with a positive charge on the plate over here. Perfect. Let's move on to question number 2. An isotope. What's an isotope? An isotope is something that's of the same element, that has the same atomic number, the same chemical properties, but different mass number and different physical properties. They said an isotope of rubidium has 85 nucleons and 37 protons. So the atomic symbol for rubidium is what? Is Rb8537. Perfect. What do they want us to find? The number of neutrons. Number of neutrons, let's say it's n, is equal to the number of nucleons minus what? Minus the number of protons. Or we can say that the number of neutrons is equal to the atomic number minus the mass number minus the atomic number. So in our scenario, what's the number of neutrons or the mass number? It's 85 minus the atomic number or the number of protons, which is 37. So 85 minus 37, you are supposed to get 48 neutrons. Perfect. We move on to part C. A rubidium atom forms what? Forms Rb+, a rubidium ion. Deduce the number of electrons in a rubidium ion. We know when it's an atom, its total charge, which is what? Which is the number of protons minus the number of electron, is supposed to be equal to 0. This is what this is if it's an atom. So now what are they saying? They're saying it becomes a rubidium ion, Rb+. That means what did they do? They took away an electron. So if the number of protons is 37 in the ion, and the number of, in the atom, and the number of electrons is 37, we will have 0. But now, in the ion, if the number of protons is 37 and they took away an electron, so it became 36, now the total charge is going to be what? It's going to be +1. So what is the number of electrons in this scenario? It is what? It is 36. Okay, let's move on to the next question. Let's give the number of protons, number of neutrons, and number of electrons. Number of protons is what? Is the atomic number, 35, 56, 17. The number of neutrons is the mass number minus the atomic number. So this is 45, 81, 18, 35, 54, 18. Now, why did I say this is 35, 54, and 18? Because again, we said that the number of electrons is equal to what? Number of electrons is equal to the number of protons minus the charge. Or the opposite, charge is equal to number of protons minus the number of electrons. So in this scenario, what do we have? For BR 8035, we have 35 protons minus the charge, which is 0, so we have 35 electrons. Then for the second one, we have 56 protons minus the charge, which is 2, so we'll get 54 electrons. And then for the last one, we have 35, oh my bad, it's not 35, it's 17. We have 17 electrons, or sorry, 17 protons minus the charge, which is -1, so minus 1. This will give us an answer of 18, very simply. We'll move on to question number 4. What do they say in question number 4? Americium is a synthetic radioactive chemical element with the symbol Am. Its atomic mass is 95 and its mass number is 24. The atomic symbol of Am is Am, 243 and 95. Give the nuclear relative charge of Am. The nuclear relative charge, or the nuclear charge, is what? Is the charge of the nucleus. And in the nucleus, what do we contain? We contain the neutrons and the protons. So the neutrons, do they have any charge? No. So we will not consider the neutrons because they don't have any charge. All the charge of the neutrons is 0. But we will, however, consider the charge of the protons. So in this case, the charge of the protons, which is the atomic number, is what? Is plus 95. That means that the nuclear relative charge of Am is 95, plus 95. Perfect, perfect. What did they say now? Explain one similarity and one difference between the isotopes of Am, which is americium. So one similarity, first of all, is that they're going to have similar chemical properties. Why is that? So let's write similarity in chemical properties. Why exactly is that? It's because they have what? They have the same number of protons. And they have what? They have different physical properties. Why exactly is that? It's because they have a different number of nucleons or neutrons, but it's preferable to say nucleons or different mass number. Okay, so they have same chemical properties because they have the same number of protons, but different physical properties because they have different number of nucleons. We'll move on to the next one. Give the atomic symbol of a possible isotope of Am. So let's take Am. What did we say about isotopes? Isotopes have the same atomic number. That means if the atomic number of Am is regularly 95, then every single isotope of Am will have what? Will have 95. Now, regarding the mass number, what also happens in an isotope? It is either that it's a difference in the mass number. But what changes? The protons don't change. They are fixed. They are 95. But the only thing that changes is the number of neutrons. They also all have to have the same charge as well. So you could give, for example, 242 if you want to go less, or Am 95, 244. These are 2 examples. You can write many more examples. Yalla. Question number 5. Naturally occurring lithium is composed of 2 isotopes, 6Li and 7Li. The average atomic mass of lithium is 6.9. Calculate the percent abundance of each isotope. So how do we do this? We said to calculate the atomic mass, right? To calculate the average atomic mass, AAM, it's equal to what? It's equal to the mass multiplied by its percentage plus the mass multiplied by its percentage. But what do we also need to know? We need to know that this percentage and this percentage, or like if you have more, all of the percentages added together will give us a total of 100. Perfect. So what could we do in this scenario? You could write that it's multiplied by X% because it's a percentage, and then 7 is multiplied by what? It's multiplied by 100 minus X%. Why is that? Because we said if we add this and this together, we're supposed to get 100. So now, what is the average atomic mass? It's 6.9 is equal to 6x over 100, which is the same as 6 times X%, plus 7 times 100 minus X over 100. You can make one common denominator, which is 100. You can link the denominators together, and then you can expand this 700 minus 7x. Now what do we do now? We will move this to the other side, and what will it become? 690. So 690, after moving it to the other side, is equal to 6x plus 700 minus 7x. Move this to the other side. This becomes minus 700 plus 690. 6x minus 7x. What do we get then? We get minus 10 is equal to minus x, so that means x is equal to 10%. Now this percentage corresponds to which one? Corresponds to lithium-6. So the percentage abundance of lithium-6 is 10%, and for that of lithium-7, it's going to be 100 minus 10%, which is what? Which is 90%. Okay, perfect. We'll move on to the next question. Question number 6. Given below the mass spectrum of a sample of unknown element. Okay? Deduce the number of isotopes. Again, how did we say we could deduce the number of isotopes? By counting how many lines there are. There are 2 lines, so that means what? That means there are 2 isotopes. Now calculate the relative average mass. How do we calculate the relative average mass or the relative atomic mass? It's the mass, 75.78, multiplied by its percentage. I'm gonna just assume this is 75 and this is 25, okay? Because we cannot take like the values to be decimal, okay? So you have to take them. So it's gonna be what? It's gonna be the percentage, which is 75% multiplied by 35 plus 25% multiplied by 37. Now, you could do it like this. You don't need to put it over 100. Why? Because you already put the percentage. Or you could do it like 75 times 35 plus 25 times 37 over 100. Either this or this, they are both the same. They both work. So in all scenarios, you put it on the calculator and you're supposed to get 35.5. This is the relative average mass of the element. Now identify the element using the mass spectrometer. You will look up, you will see which one has an atomic mass of, or like a relative average mass of 35.5. It is chlorine, Cn. So that's pretty much it for 1.2. We'll move on to 1.3. What does it say in 1.3? The surface of sodium metal is struck by electromagnetic radiation, and they said what the energy, E, of photons is this much. Using the table below, deduce the color of light that caused the electron to be ejected from the surface of sodium. So what do we know that the equation is? We know that E is equal to H times V, where H is Planck's constant and V is the frequency. Another equation we had, if you remember, is that C is equal to wavelength times V. C is the speed of light, 3 times 10 to the power of 8. Lambda is the wavelength and V is the frequency. Now, they want us to find the value of the wavelength. So wavelength is equal to speed of light over the frequency. And how can we find frequency alone? You will take frequency is equal to what is equal to the energy divided by Planck's constant. So what do we do now? We will write the equation. We'll substitute the values. V, the frequency, is equal to the energy 3.76 times 10 to the power of minus 19 divided by what? Divided by Planck's constant, which was 6.626. Let me open my notes because they didn't give it here. What is Planck's constant? 6.626 times 10 to the power of negative 34. So what do we get in this scenario? We're going to get that V is equal to 5.67 times 10 to the power of 14. Now, what do we need now? We have the frequency, and using the frequency, we can find the wavelength. So wavelength is equal to the speed of light, which is 3 times 10 to the power of 8, over the frequency, which is 5.67 times 10 to the power of 14. We will get what? We will get 528 times 10 to the power of -7. But I think they want the answer in nanometers. So how do you change from meter? Because this is everything when you calculate should be in meter. So how do you change from meter to nanometer? You very simply multiply it by 10 to the power of 9. So times 10 to the power of 9. And you will get 529 almost. Now 529 is in the range of green. That means the color of the light that caused the electrons to be ejected from the surface of sodium is green. Now what are they telling us in this one? They're telling us calculate the energy E of a photon whose wavelength is 558 picometer. 558 picometer means what? It means 558 times 10 to the power of -12, if I'm not mistaken, meters. Okay? They gave us what? They gave us Planck's constant, and they gave us the speed of light in a vacuum. So again, energy is equal to Planck's constant times the frequency, and the frequency is equal to what? Is equal to the speed of light over the wavelength. So frequency is equal to what? Is equal to speed of light, 2.99 times 10 to the power of 8, over the wavelength, which is 558 times 10 to the power of -12, right? 558 times 10 to the power of -12, and then 2.99 times 10 to the power of 8. You're supposed to get an answer which is 5.36 times 10 to the power of 17. Now, using the V, we can calculate the energy. Energy is equal to Planck's constant, which is 6.626 times 10 to the -34, multiplied by 5.36 times 10 to the 17. And you will get the energy to be what? The energy to be 3.55 times 10 to the power of -16 joules. Perfect, that's question number 8. Let's move on to question number 9. State the maximum number of electrons that can occupy the 5th energy level. We said to calculate the maximum number of electrons, we will use the equation 2n squared, where n is the energy level. So 2 times 5 squared, that's going to be how many electrons? That's going to be 50 electrons. We move on to question number 10. Write the name of the orbital that corresponds to the shape below. This is s orbital because it's spherical. This is p orbital because it's dumbbell-like. And this is what? This is d orbital because it's a dumbbell with a donut in the middle. We move on to question number 11. State the maximum number of electrons that can be found in a d subshell. It's 10. And what's the maximum number of orbitals that can be found in the 4th energy level? What's the equation for the maximum number of orbitals? It's n squared, where n is the energy level. So 4 squared, so it is 16. Perfect. Question number 13 now. What is meant by degenerate orbitals? Degenerate orbitals have the same energy and the same sublevel. State whether the following pairs of orbitals are degenerate or not. They should first of all have the same energy, 3s and 3p. Okay, that's the same energy. And the same subshell. Wrong, they don't have the same subshell. 3px and 3py, same energy, yeah? Same subshell. This is an answer. 4px, 4px. 4 and 5, different what? Different energy level, so it's not this. Question number 14. Draw the orbital notation for the following elements and indicate the atoms that are free radicals. What do we mean by free radicals? By free radicals, we mean that they have unpaired electrons. So you guys should know how to do the configuration of nitrogen, beryllium, magnesium, and aluminum. Let's do them first. First one is 1s2, 2s2, 2p3. Then 1s2, 2s2, 1s2, 2s2, 2p6, 3s2, and then 1s2, 2s2, 2p6, 3s2, and 3p1. Now, preferably, my bad, I don't know why I wasn't able to say it. Preferably, you take the very last subshell, okay? So here it's 2s2, 3s2, 3p1. This will help you save time. But in the exam, try to do all of the subshells, but preferably I would say to use only the last subshell, so you will like not waste any time. So 2p3, p, we know it's in 3 orbitals, and we said based on Hund's rule we need to fill in all of them with the same spin first. So 1 up, 1 up, 1 up, and just like that we finished. And so they are all what? They're all unpaired. And if they're all unpaired, that means they are what? They are free radicals. طيب, for this one, S is only one box. You have 1 up, 1 down. It's not a free radical, it's a full. S also has 1 box, 1 up, 1 down. Same scenario. P, 3 orbitals, 3 boxes, but it has only 1 electron. So this electron even is unpaired. So what do we call it? We call it a free radical. So that's question number 14. We'll move on to 15. Oxygen has 8 electrons. Explain why the following electron in box representation is high in energy. Perfect. We know that according to Hund's rule, when we are filling in the orbitals, we need to start first with the same spin and complete orbitals, then we move to the other spin. So for the last box, it's supposed to be like this: 1 going up, 1 going up, 1 going up, and 1 going down, because therefore it's supposed to look like this, because Hund's rule states that we need to complete all of the orbitals before we move on to the opposite spin. Now, why is it high in energy? It's high in energy because it has no free radicals. Because we know what? We know that the more free radicals, that means the more stable it is. So the greater the free radical, the greater the stability. The less the free radical, the less the stability. Okay, so that means the more free unpaired electrons, the more free radicals, means it's stable, whereas the less free radicals means it's what? It's unstable and high in energy. We move on to question number 16. Write the shorthand electron configuration for the following atoms and ions. I'm not gonna go too deep. You guys are supposed to know how to do them. For example, Fe is what? Fe is argon, 4s2, 3d6. Chromium is the exception. You guys are supposed to have it memorized. So chromium is also argon, but it's 4s1, 3d5. So what did they do? They took 1 electron from S and they gave it to D. Then Cu, it's also another exception. Argon, 4s1, 3d10. What did they do? They took the electron from S and they gave it to D. Now, Cu plus, very, very, very important. We said whenever we end with a d orbital, what do? We remove the electron from the S, right? From the nearest S. So for example, we know that it's argon, 4s1, 3d10. But they said that we took away an electron. So we always take away the electron from where? From the nearest, 3d10. From the nearest S subshell. Why? Because it ends with D. Now, Mn2 plus, it's gonna be what? It's gonna be argon again, and it ends with what? And it ends with 4s2, 3d5. But 2 plus means that they remove 2 electrons, and because it ends with D, what are we supposed to do? We're supposed to remove the electrons from where? We're supposed to remove the electrons from the S. Perfect. Now we'll move on to 17. Use the 1s2 notation to complete the electronic configuration for the following. We start with 1s2, 2s2, 2p6, 3s2, 3p6. This is all now 18. We need what? We need 10 more. So we'll write 4s2, 3d8. Just like that, we reached what? We reached 28. Perfect. Now Fe3 plus, in my opinion, do Fe regularly and then remove the 3 electrons. So it's gonna be what? It's gonna be 1s2, 2s2, 2p6, 3s2, 3p6. So that's how much? 18, 26 minus 18. There's 8 left. So 4s2, 3d6. Now what did they do? They removed 3 electrons, but because we end with D, we should first remove from the s orbital, then we can remove from the d orbital. So you remove 2, there's still 1 more to remove. You'll remove it from the d orbital and you'll be left with 5. So 3d5. Now this is 18, we need to make it 20. You just add 4s2. Aha, Se2 plus. First you change it, so 34, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, this is how much now, 20, 3d10, 30, and then 4p4, okay? But they said 2 minus, meaning they did what? They added 2 electrons. You always add it to the nearest subshell. So in this case, it's 4p. So you will add 2 electrons to the 4, and it will become what? It will become 6. Okay, so let's write the electronic configuration of SC, which is 21, and K, which is 19. SC is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Okay, so let's calculate. Is it 20? Is it 21? 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 1. That's 21. Now for K. K it is what? K it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Let's add them all to see if we have 19. So 2 plus 2 plus 6 plus 2 plus 6 plus 1, 19. Perfect. What did they say? They said give the possible electronic configuration of the atom X in GaX3, knowing that the ion of X has a full 3p outer shell. So what does it mean? Ga is 3 plus, X is what? X is 3 minus. Or no, my bad. X is minus. If X has -1 as a charge, that means it is what? That means it is a halogen, and it is in which group? It is in the 7th group, which starts with fluorine and ends with tennessine. Now, something you notice is that as you go down the group, you will notice that they all have what? They all have literally similar configurations, except that it's on a different energy level. Okay, so they have similar configuration. They all end with the same thing, except that they're all on different energy levels. For example, fluorine, not phosphorus, my bad. Fluorine is 9, so 1s2, 2s2, 2p5. Then chlorine, 17, 1s2, 2s2, 2p6, 3s2, 3p5. You see, they end with s2, p5, s2, p5, but the only thing that's different is their energy levels. Now we can make a rule that all of them end with what? They end with s2, p5, s2, p5. Now, the ion has a full 3p outer shell, not the atom, the ion. So what do they mean by ion? The ion means that you're gonna add an electron, and when you add an electron, it becomes a full outer shell. So let's do it. 1s2, 2s2, 2p6, 3s2, and 3p6. We stop here. We wrote 3p6 because this is the ion of X, but we did what? We added 1 electron. If they needed the atom, we would need to take away this electron, and we'd be left with 1s2, 2s2, 2p6, 3s2, and 3p5. So very simply, we can say that this is chlorine. We move on to 20. Electron configuration is the pattern of electrons filling the energy levels and sublevels of an atom. Label and fill the energy levels for chlorine with electrons. So we need what? We need to write, first of all, the configuration of chlorine atom, which is 1s2, 2s2, 2p6, 3s2, 3p5. This is chlorine atom. Now, we start. First thing we always start with is 1s. Right? We always start with 1s. How many electrons does it hold? It holds 2 electrons. 1 up, 1 down. Perfect. I think I need to zoom in for this one. 1s2, 2s2, 2p6, 3s2, 3p6. Perfect. We said we started with what? With 1s. We have 1 up, 1 down. Then, after 1s comes 2s. How many electrons does it hold? 2. So 1 up, 1 down. Then we have 2px, 2py, 2pz. Because there's 3, so x, y, and z. And then this can hold 1 up, then 1 up, then 1 up, because it's 2p6, then 1 down, then 1 down, then 1 down. Perfect. Then comes 3s. How many does it hold? It holds 2. Oh, by the way, 3p5, my bad, not 3p6. 1 up, 1 down. Now 3p, 3px, 3py, 3pz. So we said that there's 5 electrons. So we start by filling 1 up, 1 up, 1 up. then one down, and as you can see, this one is a lone pair. It does not have anything to pair with. So what do we call it? We call it a free radical. Perfect. That's it for this question. They said chlorine gains one more electron to become Cl minus. Draw the shape of the orbital to which the electron is added. Now we said that the last one ended with one up, one down, and one down. So it ended with one unpaired electron. So they said it gains one electron. Where will this one electron go? It will go over here. So in which orbital did it go into? It went into orbital P, but which orbital? Px, Py, or Pz? It went into orbital Pz over here. So you will need to draw on Pz the orbital, which is a dumbbell shape, like this. Okay, part C. Compare the 1s orbital to the 2s orbitals. Both of them have the same shape, which is spherical. However, their size differs. Okay, so they have same shape, but different size. Same shape, different size. As energy level increases, as n increases, size increases. Okay, chlorine tends to gain an electron and form Cl-. Write the shorthand electronic configuration of Cl-. I'm not gonna waste my time on configuration. You guys are supposed to know how to do it. So it's neon 3s2 3p5. But they said Cl-, so it gains an electron, so 3p6. Why is chlorine atom considered a free radical? Why is it considered a free radical? Because it has an unpaired electron. It has unpaired electron. Perfect. Now we move on to the last 4 questions. Hopefully they will not take time. Write the general form of Coulomb's law of attraction between charged particles as applied to lattice energy. This was the weird question, like the weird formula that we discussed, that we said that chemistry wanted to take something based off Coulomb's law, which is that energy is equal to kq1 q2 over r, not r squared. This is very simply 21. We'll move on to 22. What does it say in 22? Below is the complete photoelectron spectrum of a pure element X. Identify X and write its electronic configuration. So first we start with this over here, then this and this. These are what? 3 different energy levels. Energy level 1, energy level 2, energy level 3. First of all, we start with energy level 1, which has only S. And how many electrons does it hold? It holds 2 electrons. We move on to energy level 2, which has 2s and 2p. This holds how many electrons? 2. How many electrons does this hold? 6. Then this has what? This has 3s and 3p. The 3s holds 2 electrons, whereas the 3p holds only 3 electrons. So what is the total number of electrons? The total number of electrons is 15. And what element is this? Let's look. Which has 15? It's phosphorus. So phosphorus is our answer. Perfect. We move on to part B. Element Y is directly to the left of element X. We said when we move to the right, that means it has what? A higher binding energy. When we move to the left, that means it has what? It has a lower binding energy. So as we move to the left across the periodic table, okay, this causes the binding energy to what? To decrease, right? So when the binding energy decreases, that means it shifts to the right a bit. So if we were to draw it, it would look something like this. Here we go. That's question 22 done. Let's move on to 23. Explain the photoelectron spectra below, which show the amount of energy needed to remove one s electron from N and O atoms. Now, very simply, nitrogen requires less energy than oxygen. Why exactly is that? Very simply, this is because oxygen has what? Has a higher nuclear charge, and this higher nuclear charge will exert a stronger force of attraction on the atoms. So O, higher nuclear charge, stronger attractive forces, thus requiring what? Thus requiring more energy. Perfect. We'll move on to 24, the last one. Given below is the photoelectron spectrum for neon. Okay, what does it say? It says, explain the relative position of each peak and its size. This peak is 1s2. This is 2s2, 2p6. Now, the size. will determine the size or the height of the peak will determine what will determine both the sub-level and the number of electrons. So we always start with what? With 1s. This we can know. First of all, we start with 1s. Now, based on the height, we can know the number of electrons. Again, same thing. This is 2s to p. Based on the height, we can infer what? We can infer the number of electrons. Now, the relative position. Why is 1s so far and 2s and 2p so different? Very simply because 1s requires more energy to remove the electrons from this orbital versus 2s, 2p, they need less energy. Why is that? 2s and 2p are very far away, like farther away from the nucleus, so it's easier to take them out. You don't need too much energy to take them away from the nucleus. But however, regarding the 1s2 orbital, because it's really close to the nucleus and the nucleus will be exerting the most force of attraction on it, we will need so much energy in order to overcome it. And perfect, that's it for chapter 1. Thank you guys for watching. I hope you enjoyed and have a wonderful day.